Hello, my name is Dan Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos I've been posting on the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you how I've completed a couple of the projects. So I've got some videos on the forum showing me going through Project 1 and its associated circuits, and I've completed the coding challenges for each of the circuits as well. I've put videos on the forum for Project 2 as well, again going through all the circuits associated with Project 2 and the associated coding challenges, and I've started to do that for Project 3. So I've got two videos on the forum, one of me going through the first circuit in Project 3, Circuit 3A, where it deals with servo control, and I've done the coding challenge, and then I have another video out there for Circuit 3B where it introduces the ultrasonic sensor, and I've done that circuit and the coding challenge for it. And in today's video, we're going to be going through Circuit 3C of Project 3, which is the final circuit in Project 3. And I'm going to go through the actual circuit itself that you'll see in the SparkFun Inventor's Kit Guide. And then I'm also going to show you the coding challenge that I've done for this one, where I create an interactive Nerf gun using an ultrasonic distance sensor, RGB LED, servo motor, and a buzzer. I'll start by introducing the components that I'm going to use. So I'll be using an ultrasonic sensor for measuring distance, the RGB LED to provide visual feedback, a servo for action, and the buzzer for sound alerts. And I'll also explain how each component is connected in the circuit, specifically the trigger and echo pins of the ultrasonic sensor, and the 3 pins controlling the RGB LED. In setup, I'm going to initialize serial communication and configure the pins using pin mode functions as usual. And in particular, we're going to be introducing a bipolar junction transistor. This is an electrical component that I'm using to control the power to the Nerf gun mechanism. So I'll be discussing bipolar junction transistors as well as MOSFETs in this video as well. In the loop function, I'll briefly explain how to calculate and print the distances measured, and we'll use the getDistance function to trigger the ultrasonic sensor and interpret the code. We've shown that in previous videos. And then I'll discuss the conditional statements determining the actions based on distance. So we're going to turn the RGB LED red for close proximity, so meaning if there's an object close to the ultrasonic distance sensor, or the ultrasonic sensor rather. We're going to have a yellow for medium and green for far away. And we're going to do this while controlling the servo and buzzers accordingly, depending on the distance. Then I'm going to demonstrate the functionality of a fire button that activates the Nerf gun and provides immediate feedback through the serial monitor, although the actual feedback is going to be the Nerf gun firing a dart. Lastly, I'll share the challenges and troubleshootings that I faced during this coding challenges, which were many. It was definitely a challenge for me. Especially understanding the BJTs and wiring issues. I had a lot of that. I had a lot of components, and it caused some issues. So without further ado, let's get right to it. So I think we're around page... Let's try 64. Okay, so as I said, if you watch the previous videos, you'll see that we completed Circuit 3B, where we introduced the distance sensor. Now we're on to Circuit 3C, motion alarm. And if this is the first video you're watching that I've put out, I don't read the thing in entirety. I just kind of read the highlights and discuss things as I see their relevance. So, in this circuit, we're going to use light, sound, and motion. So, the light is the RGB LED, the sound is the buzzer, and the motion is going to be the servo motor. So, the servo motor we're adding so that we can add a moving pop-up to animate your alarm. So, I'll show that in a minute. The components we're going to use, an RGB LED, which we've used before. So, the RGB LED has 4 leads, 1 common ground, and then a separate lead for each of the smaller LEDs that are in the RGB LED. So an RGB LED is actually made up of 3 separate LEDs, a red, a green, and a blue, all housed in this one LED unit. Because we're dealing with 3 separate LEDs in one unit, we do need 3 separate resistors, so 330 ohm resistors, because again, anytime you have an LED in a circuit, you do need to put a current limiting resistor with it in order to prevent too much current from going in the LED and making it really bright for an instant and then burning out. We're going to be using the piezo buzzer for sound, a lot of jumper wires, and a servo motor. As well, we're going to need some tape, paper clip, needle nose pliers, markers, paper, scissors, all that sort of stuff, which is not included in your SparkFun Inventors kit. So we're going to be using that to make our pop-up, which is what our servo is going to control. And we're also going to use the distance sensor. So the mechanisms that are going to be new concepts for us today is we're going to use the servo to animate something. So we're going to connect our servo to some physical mechanisms. In this case, it's going to be a paper clip and a cutout paper. So something like this. So because we're going to do that, we're going to need to create linkage rods and things like that. These are commonly used in remote control airplanes and other different things, remote control boats or anything like that, really. And we're going to have to create one out of paperclip. I'm not going to go through the assembly of it. This basically, if you read this, it tells you how to take a paperclip and bend it so you can get this linkage rod and then attach it to your servo motor. You can see it here. Then it says, print off a picture. You can either get this picture of this menacing cat and cut it out to proper dimensions, about 2.5 inches by 2.5 inches, with this extra paper to tape under the breadboard. I chose to use a different image myself, but maybe I'll try to pop that up and show you what I'm using. Do I have it here? Okay, I'll just show you the image I have here. Actually, just taking a second to pop up. So this is the image that I'm using for mine. You can use whatever you want. You can use that cat. This is a sassy donut. And she's, because I don't have the issue, I do have a cat, but my cat doesn't jump up on the counter, so I have no need to scare the cat with a motion sensor alarm. But I am trying to curb my snacking and going to the fridge needlessly, so this little vixen here is going to hopefully help me with that. Then it shows kind of the circuit. So this is kind of what's happening. If you can see here, attached to the servo motor is this linkage rod that is just made from bending a paper clip, and it's attached to the backside of this paper cutout of the cat. So before we go to the hookup guide, I'll show you my paper cutout. So again, on the circuit I've got here, I've bent a paper clip and made this linkage rod. Again, this just 90-degree bend and attached to the servo motor. And there is the sassy donut. So again, she says, do not even think about having any junk food. Hopefully that'll help me curb my my bad habits. So as usual, the SparkFun Inventors Kit Guide has a great schematic and for you to hook up everything. So we've went through a lot of this in previous videos, how to hook up the ultrasonic sensor. Again, you've got the power and ground connection, as well as your trigger pin and echo pin. They're connected here. You have your piezo buzzer, which one end is connected to ground, the other end is connected to a, in this case, the pin number 10, pulse width modulation pin, in order to output sound. I've actually have mine hooked up through a potentiometer, which I've shown in previous videos, is used for volume control. Hooking it up this way is fine. It just means that the buzzer is going to be on at full volume all the time. And using a potentiometer, I can control the volume, so I have one additional component here. And then your RGB LED is hooked up through the common ground, and then each of the individual leads for the red, green, and blue LEDs are hooked up to PWM pins. In this case, pins 3, 5, and 6, which are all PWM pins. And then I have my servo motor connected to the power and ground rails of the breadboard, which is ultimately connected to 5 volts and ground of your microcontroller. And the signal wire, which is the white wire, is connected to a PWM pin. So that's important. So that's what the circuit diagram looks like. And I'll just show you my actual circuit. So if you can see here, the RGB LED, again, I've got a common ground connection on this side connected to the negative rail of the breadboard, And I've got the negative rail on this side connected to this side through this gray wire, and the positive rails connected through the red wire. And then I've got 3 current limiting resistors, 330 ohm resistors, connected to 3 wires. Obviously the colors of the wires correspond to the LED. So this would be the red LED, green and blue, and those are connected to your PWM pins, 3, 5, and 6 respectively. This is my piezo buzzer. Again, one end of it is connected, instead of ground directly, it goes into one of the edge terminals, so the left terminal or first pin, however you want to call it, of the potentiometer, and then out through the wiper I go to ground. So the piezo buzzer is effectively going to ground, but it's going through this middleman first, through the potentiometer, and that just allows me to control the volume of the buzzer. The positive end, denoted by this little positive symbol, is going through this purple wire into pin number, well, let's take a look, pin number 10, which is a PWM pin, as required. And then, as usual, the ultrasonic sensor, I've got the green wire is ground, the red wire's power, and they're just hooked up to the power rail of the spreadboard, which is, as you can see, connected to the Arduino's 5-volt and ground. And then the orange and yellow wires representing the trigger and echo, because you can see on the front, trigger pin is the orange, echo is the yellow. They're connected to pins 11 and 12. And then the servo motor, I've got the power and ground hooked up again to the breadboard, power and ground rails, and the signal hooked into pin number 9 through that white wire. So that's the physical circuit. We'll just talk about what's happening in the circuit. Basically, the RGB will behave as your last circuit. If you're right next to, in front of the servo, in front of the ultrasonic sensor, the LED is going to be red, and this time the servo is going to be moving back and forth frantically, having this cat essentially looking like it's lunging at you, or just having a seizure or something, I'm not sure. And then as you step away, it'll turn yellow, the RGB will turn yellow, and then if you're really far from the ultrasonic sensor, it'll be green. And again, the cat will only be jostling back and forth if you're right in front of the ultrasonic sensor, in which case the light will be red. This is the overview of the program. Let me just make this bigger. So again, if the distance is less than 10 inches, the RGB is going to be red, and the servo is going to rotate back and forth, and the buzzer is going to beep. And if the distance is between 10 and 20 inches, the RGB is going to, LED is going to be yellow, and the servo motor is not going to do anything, nor is the buzzer going to beep. And same for if neither of those conditions are true, meaning you're beyond 20 inches, the object is beyond 20 inches in front of the ultrasonic sensor, the RGB is going to be green, and nothing is still going to happen. Let's just look at the code quickly. So, I'm just going to make this code a little bigger so we can quickly look through it. So as usual, the multi-line comment here tells you what the program does, which I already discussed, and you can get the circuit diagram and instructions and the code. So because we're using the servo motor, we need to include the servo library, and then we're also going to have to create an instance of the servo, typically called my servo. This is just a common convention, but you could name this anything. You could have a servo called Bob if you want. In setup, we're going to call the attach function on the servo object we created, so myservo.attach, passing in the number that representing the pin that we've attached the servo to. And we've attached ours to digital pin 9, our PWM pin, which is why it's there. This attach function, as I've mentioned in previous videos, is essentially pin mode, but it's how the servo library does things. Instead of calling pin mode and you pass in the pin and then call the servo motor as an output, you just call this attach function directly. So again, you'll notice that they're using a magic number 9. Again, I'm just using the program that you can download from their website, but it's not good programming practice to have magic numbers. That would be better if that was something like just a constant that said, something like servo pin, the way this says buzzer pin, and these are RED, red pin, green pin, and blue pin. And then, so that's it's set up. Then what ultimately is going to happen with the servo motor is if you're within 10 inches, if the distance is less than 10 inches, what we're going to do with the servo motor is we're going to call the right function on the servo motor and pass in a certain degrees. In this case, I'm passing in 160 degrees. That'll be different depending on how you've set it up on the board and everything, but this works for me. So I'm going to remember the limits of a servo motor can go between 0 and 180 degrees. So I'm at almost one limit. And again, you don't typically want to go between the extremes because a servo motor can get jittery and not respond quite as you like. So I'm going to 160 degrees. I'm going to delay by 100 seconds, stay there, 100 milliseconds, so 1/10 of a second. And then I'm going to change the position of the servo motor by writing it to 140 degrees, so just moving it by 20 degrees, delaying for another 1/10 of a second or 100 milliseconds. And I'm going to do that back and forth over and over while the object is within 10 inches. So that's just going to create an effect where your cutout just goes back and forth, looks menacing. If the distance is not within 10 inches, meaning you're between 10 and 20 inches, I'm just going to have the servo go to 20 degrees. Again, this is just something that I'm putting my cutout as down a little bit so you're not really looking at it too much. And I put it to that same position. For if you're really far away from the object as well. So basically, the only time I'm moving it is if you're within 10 inches of the ultrasonic sensor. The comments here don't quite match up. They say move the servo to 135 degrees. Obviously, I have it at 20 degrees. I think I changed this slightly from their... so you'll notice I named the code. Circuit 3C motor alarm slightly modified. So I took their code and slightly modified it. And those slight modifications are the positions of the servo that work best with my circuit. So that's what's happening with the servo. I'm just kind of going through this element by element. Now this code is associated with your ultrasonic sensor. I create two constants, trigger pin and echo pin, on pins 11 and 12 respectively, for use in my ultrasonic sensor. I've created this float global variable, so distance, which is of type float, set to 0 initially, and this is going to store the distance measured by the sensor. In setup, I call pin mode as usual, setting up my trigger pin as an output, because again it has to send that 10 microsecond output to start things going off, and my echo pin as an input, which is going to receive a high pulse that's proportional to the duration of time it took the signal to hit an object and come back. This has all been explained in previous videos, so I'm just kind of going a little quicker through it, at least quicker for me. In the loop, I'm calling the get distance function and then assigning that return value to a distance variable, which is that global variable we created. And I'm printing out the distance to the serial monitor along with the unit of measurement after it, inches. So because it's in inches, that means our calculation is going to be basically taking that duration that's in centimeters per microsecond, that duration which is in microseconds, and dividing it by 148 to get inches. That's just a side note. And then all of this code is associated with the ultrasonic sensor as well, because we're basically using these conditionals to determine what actions we take. If the distance is less than 10 inches, well, that's when we turn on the red LED and we basically wiggle the servo motor back and forth and beep the buzzer. And if the distance between 10 and 20, we turn on the yellow LED by having both these colors activated, and we don't have the buzzer on, so no tone on buzzer pin. We shut off the buzzer and we move the servo motor out of the way to 20 degrees. And else, so meaning else, which is going to happen if we're not within 10 inches and not between 10 and 20 inches, so therefore when we're greater than 20 inches, that's when the else happens. So if the object is far away, in which case we're going to turn on the green LED, again writing 0 for the analog writes for the red pin and blue pin, only turning on the green LED fully, and again, we're going to keep the buzzer off and put the servo to the way by going my servo.write 20 degrees. And then we're just delaying 50 milliseconds every loop so that we can properly read things on the serial monitor. We've went over the distance function in previous videos. This just returns the distance measured by the HC-SR04 distance sensor. Basically, it's a function that takes no parameters but returns a float. And we've got a couple local variables as soon as we come in representing the echo time and the calculated distance. The echo time stores the time it takes for a ping to bounce off an object, and then the calculated distance actually calculates the distance based on that echo time, that high pulse. So first thing we need to do is we need to send out an ultrasonic pulse that's 10, it says milliseconds in this comment long, but that should be microseconds. So they're off by a couple orders of magnitude. So what we're going to do is we're going to call the digital rate function on the trigger pin, and then set it high. For delay, 10 microseconds. So again, this is a delay function called delay microseconds. Again, not milliseconds, but microseconds. And we're going to do that for 10 microseconds and then set it low. So this is our ultrasonic sensor sending that 10 microsecond pulse out on the trigger pin, and then the echo pin is going to read that in using the pulse in function, which takes in two arguments. The first one is the pin that we want to read this in on, the echo pin, and high mode. So that's something that we don't control. The sensor that we're using, the HC-SR04, the echo pin is based on a high mode function, so some other sensors might work on low. So this is just something you have to put when working with this sensor. And we're going to assign that to our variable echo time. If you watch my previous video on the ultrasonic sensor, you'll know that there are better things to do than pulse in. It's better to use time functionality because pulse in has the same detrimental effects that delay does, in that it stops the execution of the code. So just like delay is a quick and simple way to do debouncing when you have a button press and you want to add just some functionality to have a debounce, you'll just add a delay. It's not the best thing to do. It'd be better to use time functionality and to achieve debounces, but a delay works most of the time and is simple enough to implement. Well, pulse in is kind of akin to that. There's better things that we could do using time functionality, but pulse in will get the job done, and in this code it's not going to be the end of the world. So after we have that echo time, we're simply going to calculate the distance by taking that echo time, which was the duration of the high pulse for a certain duration, proportional to the distance it took to hit an object and come back. We're going to take that echo time and divide it by 148. And that'll give us a distance in inches. That 148 is in inches. If we wanted a distance in centimeters, we would have had to divide by 58. And if you're interested in how those calculations come to be, either look at the datasheet for the HC-SR04 or watch my previous video on the ultrasonic sensors, and I go through those calculations in more detail. And then you're just going to return that calculated distance. And finally, we haven't been through the buzzer pin and the LEDs, but these constants are just associated with the three LEDs, the red pin, the green pin, and the blue pin. Again, these are all housed in a single RGB LED, but they're three separate leads. So they need three separate pins, and they're all on PWM pins. The way we have the code set up, we need that. And then we have the buzzer pin on pin number 10. So that pin is going to drive our buzzer. It's going to sound when an object is within 10 inches. We just have our pin modes for those. So all of the LEDs and the buzzer pin are set up as outputs. And again, if the distance is within 10 inches, so if there's an object really close to our ultrasonic sensor, apologize for that. So just going to have to reset things. I had an alarm go off and it just shut down my webcam. And by webcam, I just mean my phone. Perfect. Just making sure it's back. So I don't actually have a webcam, so I just use my phone. And when an alarm goes off, it screws things up. So, as I was saying, if the distance is really close, if the object's right in front of the ultrasonic sensor, we're going to call our analog write 3 times on our red pin, our green pin, or blue pin. In this case, we're only sending out a value via analog rate on the PWM pin on the red pin. So we're sending our full value 255. Again, analog rate, the second argument can be a value from 0 to 255, indicate from 0 volts to essentially 5 volts. So we're sending all 5 volts to the red pin, making a bright red, but nothing to the other colors. So this will just be red. And this is the code again that wiggles the servo motor back and forth and beeps the buzzer. So we call the tone function on buzzer pin for 272 frequency, just a random frequency. We move the servo to position 160 for 1/10 of a second. Then we turn off the buzzer, so calling the no tone function, and move the servo 20 degrees ahead to 140 and for 10th second, and we keep going back and forth. So the buzzer is going to be on, off, and the servo motor is going to go back and forth between 160 degrees and 140 degrees. Again, just moving that cat. And if we move a little back, if the object moves a little back from the ultrasonic sensor, so now it's between 10 and 20 inches, then we're going to make a yellow color with our LED by writing 255 to red and writing 50 to green. So that's about 1/5 of the 5 volts that we're going to, so 1 volt approximately, we're going to write to the green pin, and that mixture should give us a nice yellow, and still nothing to the blue pin. And then we're shutting off, we're not going to have the buzzer sounding if the distance is between 10 and 20 inches. So there'll be no sound, and we're going to move the servo out of the way by writing it to angle 20. So it's out of the way. And again, there'll be no sound if we're past 120, or sorry, if we're past 20 inches, there'll be no sound. And again, we keep that servo motor at 20 degrees out of the way. And we're going to just write something to the green pin, a full 5 volts, 255 to the green pin. And so that's pretty much the code. Again, if you want more detailed explanation, feel free to read the guide or watch any of my previous videos. But we're going to just upload this code and see it work. So I've already got the code still on here. Okay, remember if this code, yep, so we're just going to be printing out the distance. So before I re-upload the code, I'll just show you how this is working, and then we'll re-upload the code. So as you can see, the light is green, nothing's happening. The servo, you can see that there's a slight angle to the paper cutout, so it's kind of, if you were walking towards it, if I was walking towards the fridge, I wouldn't necessarily see it fully. Again, you could make that even go down even further if you changed the bends in your linkage and how you created this thing with a paper clip. But in this case, it's kind of out of the way. There's no buzzer going off in screen. As I come closer, so as I get in yellow, still no sound. So I'm closer, still no sound, the servo motor's not doing nothing. But as I get closer and closer, then as you can see, the servo motor is jostling back and forth between that 160 and 140 degrees, and the buzzer is sounding. So if you want to see what that looks like from this angle, probably put this the right way up. So that's what you would see if you were walking towards the fridge and you were having a snack when you probably shouldn't. So nothing's happening. This will be out of the way, and I walk towards the fridge, and don't even think about having a snack. So that was the code up there. I could re-upload it now. It's not really necessary, but we'll do it just so you can see the distances. So as you can see, the distances there, So we'll just verify the distances are working out good. So if I'm outside at 20 inches right here, I'm green at 20 inches. As soon as I come within 20 inches, yellow. And then once I pass 10 inches, we're going to go red, and this is happening. Go back out to 10 inches, we're good. So that's that circuit. So that's the basic circuit. And I'm just going to unplug this. And then, so the code denote of that is we have a lot of constants. Constants are just variables that have been marked as read-only and you cannot have their value changed. And so that's like your pinouts that you'll often do. So our button pins or buzzer pin, anything that we know we're not going to change in the code, we should make constants. Declaring pin number variables, for example, that you know aren't going to change throughout the program. We use the no tone function. We talked about this before. It just takes a single argument, whatever pin number your buzzer happens to be on, and it just stops the buzzer from making sound. Because when you call the tone function, you can pass in 2 parameters or 3 parameters. If you pass in 2 parameters, you're passing in the first argument to the tone function is the pin that the buzzer's on. And the second argument to the tone function, so the first argument is the pin the buzzer's on, and the second argument is the frequency that you want to output. But in this case, so this tone will happen forever as long as the code is going, in this case 100 milliseconds, because that's what we've delayed for, before we call the no tone function. But if I didn't call this no tone function, the buzzer would just keep buzzing the entire time of the program. So you require this no tone function to stop the sound if you only pass 2 parameters in, 2 arguments into this function. You can pass an optional argument, a third argument, and you can see it's showing frequency in hertz and duration in milliseconds. So the third argument, if you pass it in, is the duration. Now if you pass a duration, you don't actually have to call the no tone function, but a lot of times people still do. It's just more explicit. You are really saying, hey, I put in a duration here, but I am also just calling no tone after a certain delay. So again, as this says, the tone function takes 3 parameters, a pin number, a frequency, and a duration. However, you can leave out the third parameter and the tone will play until you change it or turn it off. The no tone function turns off the pin that is activated with the tone function. So this is the coding challenges. The code I just showed you is the basic circuit 3C. There's no challenge to it. This is what the coding challenges are for this thing. It's a little different than normal. They're not as explicitly just do this. So this one says change the servo behavior. Just try changing the way your servo behaves when the distance sensor is triggered. I didn't bother doing this coding challenge. I normally have done all the coding challenges, but it's fairly simple. If the servo motor can be ridden from 0 to 180, not a whole lot I'm going to do with that, besides just making it jostle a little different, but then I'd have to make new linkages. That didn't seem that interesting to me. I could also change the alarm settings. So try altering the code so that the alarm goes off much further or closer away. Again, that's just changing a couple numbers literally in the conditionals. So that would just be changing, instead of saying having the buzzer go off within 10 inches, I could change this to 30 or 20 or just something more than 10, and then I would just change these values accordingly. This one obviously to match whatever this got changed to, and this just to be some further value. But again, that didn't seem that interesting. That just seems like very intuitive if you wanted to do that on your own. So that didn't seem like much of a challenge. This one did seem like a challenge, and actually was for me, which was to add a second mechanism. So instead, time to use your imagination. Basically, just try to make different objects move with your servo motor. So don't have a cat? Well, make an interactive pop-up story. Room alarm or something. So this was just try to make different objects besides that pop-up move with your servo motor. So I did that. I also went beyond that a little bit and kind of went down a rabbit hole with trying to make basically if I came to get a snack, instead of just having a pop-up and that sassy donut tell me not to have a snack, I wanted to shoot myself with a Nerf gun. But then in research, you can't just shoot a Nerf gun with an Arduino very well, or there's back EMF, there's a lot of stuff. So I basically had to learn lots of different things. MOSFETs, BJTs, bipolar junction transistors, make different circuits, practice, and then ultimately got to it. So I'll kind of just show you guys what I did, and then I'll show you the circuit, the coding challenge, and then we'll have to do it in go through it in another video because this video will be pretty long. But basically, this is I had some old Nerf guns hanging around from my kids, and this one came out of an electric Nerf gun that had battery-powered Nerf gun, and no one uses the Nerf guns anymore. And this one didn't actually work. The motor still works inside, but the gun didn't. So I tore this mechanism out, which basically is just essentially a motor. There's some connections in there. I've just put electrical tape over so I wouldn't touch them. But essentially it's got a positive and negative lead, and when the motor goes, these little discs on both sides just spin, and therefore it shoots a dart out. And so I just mounted it on this little bracket from one of my kids' science kits, and I created this, which is a mess, but in the other videos I have a neater version to show you. But essentially what this mess is this is a BJT, a bipolar junction transistor. I'm not sure if you can see it there, but it is a TIP 122, and basically it just it acts as an electronic switch, allowing me to use the microcontroller to electronically turn this on or off like a switch, and therefore turn on a motor. There's some other components in here. This is a rectifier diode or a flyback diode, and it's basically to protect when a motor or something like this goes off and generates a lot of current. It can send it back, like send the voltage back through the transistor, this BJT, which could ruin it. So this little diode, it's in kind of the reverse order, polarity, as everything else. So that way, if the electricity, the back EMF tries to be generated, it will actually have a route to go to get to ground. So you put this in the opposite way, which I'll explain in the next video, as a protection method to protect this transistor and your microcontroller for that matter. And this button I just put on there as additional, so I could either control it via the circuit, like basically if you get within 10 inches of the ultrasonic sensor, this will essentially use this as a switch and turn the Nerf motor on, or I can just press the button myself just to do it. I also have this additional servo motor, and basically the reason I have it is because even with an external power source, which I was powering this with 9-volt batteries or a 9-volt external power source, because again, with a motor you don't want to necessarily just be powering it off of your Arduino, and 5 volts wouldn't really work that great for this anyway. But I found that when I put the dart in, so the way the dart works is you put the dart in the front and it comes out the back, but the motor, even with 9 volts through it, wouldn't push this through. It would just get stuck here. Like these things wouldn't spin enough to move the dart, so you kind of have to push it on the end. And I assume there was a mechanism in the Nerf gun before it tore it apart that pushed on that, but I kind of had to destroy the plastic housing of the Nerf gun to get this out. So I can just push with my finger as the thing's going, but instead I decided to create a servo motor that with this little, I kind of just attach this weird little thing. This is actually just the end of another Nerf dart, and it acts as a plunger, and essentially when the motor turns on, this also moves and pushes the dart through. So that can all be discussed in another video, but in the meantime I might just try to set it up really quick and see if I can get it working for you guys. I say that somewhat hesitantly because I had it working earlier, but then I tore it apart, so hopefully we can get thought turning down the volume would help, but okay. I'm just going to upload the code on this first on the board and then unplug it, and do a bunch of connections. So again, if you want to stop the video now and just wait for the next one, that's fine. If not, I'm just going to do a live hookup so you guys can see it. And yeah, I'm just going to do a live hookup so you guys can see me hooking this mess up. And we'll and then hopefully see it work once. And then I'll actually explain it in more detail in a following video, going through MOSFETs, BJTs, and that sort of thing. Okay, so live hookup. It's going to take me a second to think about how this goes, but essentially, try to explain as I'm going. This button is connected to ground. One of the pins of that button is connected to this brown connection, and this black wire. You can see these are both ground. So that brown is ground on this little breadboard, and then this other pin is connected. This other pin is connected to this little red jumper, which then goes through this resistor. So this is the would be the positive lead. So this is going to be your 5 volts going through this pin of the button, and then this other one goes into that brown and black. So that's ground. So that's ground, and this is positive. Now you can see I have a pull-up resistor, which is just I think a 10K resistor that I'm using to tie this button up to 5 volts. So again, this one of these wires will just hook up to the 5 volts of the Arduino, or in this case I'm just going to hook it up directly to this rail here, because this rail is hooked to this positive rail, which is hooked to the 5 volts of the Arduino ultimately. So that's where that one goes. Also, we're powering this little servo motor off the 5 volts from the Arduino, and that's fine. Tiny little guy. This brown wire of the servo motor. So again, the servo motor has red, brown, and yellow. Yellow is the signal wire, brown is the ground, and red is the power, 5 volts. So the ground wire of the servo motor is connected right here, again attached to where this brown wire goes. They're both attached there, along with this black wire, because this is all ground, this one pin, this one vertical column. And this will be my plunger. This signal pin will get connected somewhere on the code. I guess I'll have to look and find out where. So the plunger servo motor, actually I don't have it in the code per se, because I think it's just the servo motor that's acting. So this was the code I had for the wiggling back and forth, because I've just kind of modified. I've done a little different than I normally do. Normally I restart the whole code. This I've kind of modified what they already had, just because I spent my time learning a lot of other stuff about the MOSFETs and whatnot. But this was the code that wiggled the servo motor back and forth when you're within 10 inches. And I've just commented that code out because I don't need to do that this time. And instead, I'm doing a digital write to the pulse width modulation pin that's connected to this BJT. This BJT transistor here. I'm going to write the servo to position 30, which is this little plunger. So I'm just going to remove the pin where this servo is currently in, the one that has my picture of my sassy muffin in there. I'm just going to remove that and put this servo right in its place, which was digital pin 9. So I didn't rename it, it's just the original servo motor. These two wires, by the way, are for my external battery. So this red pin, which is connected to this red rail here, is for an external battery source, 9 volts, and this black one here. So that's off the camera, but these alligator clips are hooked up to a 9 volt power source. So I'm just going to hook that up and hook that up there. I understand this is a mess of wires. These two connections here, this white and black cable connected in there, this goes to the motor. Black goes to green for ground, just because that's the color that was already in there, I believe, in the Nerf gun. And red for power, or red's going to white in this case for power. And then I've still got a couple wires here. I've got this green wire coming out. It's connected to the positive lead of the battery. So again, one end of the battery is connected to ground, the other is connected ultimately to the 5 volts of the Arduino. And this pin is also connected to that 5 volts. And again, I'm using the pull-up resistor, so it'll be held high when it's not pushed, low when it's pushed. So this button has to go, or this green wire has to go wherever I have my button pin, which if I look at my constants, the button pin, which is the fire pin, by the way, because to fire the dart, is pin 7. I don't need a pulse width modulation pin or anything like that, so I just went with pin 7. I understand this is a mess of wires. It'll be neater when we do it in the next video. This yellow wire, this is your high output pin for your BJT output. So this BJT output pin, which is pin 10, so that'll go there. So I do have something currently on pin 10, it looks like. And what is that? On pin 10, I currently have this the buzzer wire, so I'm going to remove that. We still are going to have the buzzer. I need pin 10 because I need a PWM pin for this BJT transistor. And I don't need a PWM pin for a buzzer, because as you may recall from a previous video, the tone function kind of works like PWM in a sense, but it actually can be hooked up to any digital pin. So I'm going to reallocate to pin 10 for my output pin for this BJT transistor. This is just a ground connection. It ultimately needs just to get hooked to a ground anywhere. So we can hook up to the common ground here if we want, over here on the breadboard. Again, I understand this mess of wires is hard to follow. And the buzzer pin we have to now relocate to pin 8. That's where I have it in this circuit. So that looks like it should be everything. I had a little thing for this to sit on, so that like I kind of had this mounted, but like temporarily mounted with some zap straps. But I've since then taken that off, so I'll just hold that for this demo. But we're ultimately going to just do something like this. See if I can get all the pieces here. Not sure how much of this you're going to be able to see, but we'll give it an attempt. Oh, I forgot to put on my power source. So I'm just... So now we'll just upload this code because I'm not sure it's actually uploaded. So we'll just upload this quickly. Hopefully it uploads. Okay, so I'm going to put that code down for a minute. So theoretically, right now, I guess the light is yellow because we're close to things. So there, move it back a little bit. So the light is green. We're at least 20 inches from things. If I move closer... Oh, this is, by the way, why I got inspired for the Nerf gun. I was looking at the Black Friday deals, and this was in the flyer. So if I get closer, within 20 inches, and then when I get within 10 inches, the motor should go off. Hopefully it does. Okay, so I guess this was out of camera, so I'll show this again. This servo motor also moved, acting as a plunger, so I'll just show you. So that moved. The thing goes... this plunger moved, which would ultimately, if you set it up properly, would be used to push a dart through this motor. If I had more connections where I could have the servo motor still on, the servo motor would still work as well, because the code still allows it. I just allocated too many pins, so I couldn't have that work because I lost PWM pins. But if you were using an Arduino Mega or something with more pins, you could definitely accommodate that. So this not moving is just a matter of I ran out of real estate. But if I had another pin, this would be moving at the same time. I'm going to show you with a dart. I'm going to try to do this all at once. Again, by the way, this button, even if something does, I can just press it and it'll work as well. So the button I just put there for my own testing purposes, but let's see. I think I'm going to put this dart in. I think it was like this. Can't remember how I had this mounted. I want to say it was like this though. Well, let's just try it. So you can see how the dart in there now, you didn't hear this at all because it physically can't move with that dart in there. Okay, so I think I had something like this, and I'm just going to hold this and represent how it would be mounted. No, I don't think it was like that. Maybe it was like this. Nope, obviously not like that. I'm going to try one more time to show you this. Okay, so you would have this mounted fairly close, so this moves just a little bit and would hit the dart. So we'll try, hopefully it works this time. So I lost half the plunger, but the proof of concept is there. You basically would set this up to the servo motor moves and plunges some at the same time. You could get a linear movement too, that would be better if you had that, but I'm using what I have, servo. And you just need it to push a little bit, so you would have this mounted as close as possible, so that way when you activated it, the servo motor moved. It's hard for you to see, I know, with my hand in the way, but the servo motor moves just a little bit. Just a little bit. And that little bit, I'm going to put the servo motor off to the side. That little bit of movement just acts like this and just pushes the dart through. So I'm going to activate this with one hand and push. My finger is going to act as a servo motor. And I'm going to do it again just by pressing the button so I can have one hand free. So again, pressing the button. Oh, that didn't work out at all. So as you can see, you need that servo motor to push the dart, because otherwise it just won't work. So this would be better with two people, obviously. Okay, and now. And we'll do one more. I'll have a better setup in the next video because this actually shot like 20 feet earlier, but it's hard for me to without this plunger and hold it and activate at the same time. But again, ultimately what's happening is that little plunger is moving forward just enough, and again you have it right next to it. Oh. You would have this like right next to it, so the plunger is going to fully activate. But that's proof of concept. Again, if you mounted this properly, you have the dart in there, you have the plunger working, it's going to shoot the dart with enough force. So if the dart in this case is just in there a little bit, it doesn't really have a whole lot of force, which is just why it kind of falls out. So it barely moves it. So you do need that little push when it starts. Ultimately, to get that, you want this dart like halfway through. But just try one more. I'm going to try the last one. If you've stuck this long, you'll realize that. Okay. So there you go. So that's basically the main point of this, though, was just to show you that again, you can use these BJTs, transistors. It allows a microcontroller like an Arduino or this red board here, which is Arduino type microcontroller, to use this BJT like an electrical switch, and then power something that demands a lot of current that the Arduino wouldn't be able to do. There's some protection mechanisms here, that little flyback diode. But basically, yeah, it allows you to have a microcontroller control a high current device. So this was what I did for the coding challenge. I'll show the code in the next video. I just wanted to show the demo, and this video is already way too long again. But if you follow up for the next video, I'll go through a lot of stuff, show you really everything you need to know about the MOSFETs and BJTs. So if anyone's familiar with DroneBot Workshop, they have a great tutorial that really, like, it's 40-minute long, but it goes through all the stuff you need to know about different types of transistors, bipolar junction transistors, MOSFETs, these metal oxide semiconductor field effect transistors. They basically kind of are the same thing, depending what your application is. It goes through understanding fully what is happening. Basically, a BJT is allowing you to use low current is applied to the base, just this little part of the switch, and it allows high current to flow from a collector to the switch. It allows, basically it's acting like a little shutoff valve. I put a little bit of current using the microcontroller into this transistor, and then it allows a lot of current to flow through something else, i.e. for the motor. MOSFET works similarly, but if you follow the next video, I'll go through all the stuff in detail, exactly the differences when to use MOSFETs versus BJTs, and then I'll go through some coding. Some of this code isn't as applicable. I was going to introduce a manual controller, which I might do in a further video, and use the wireless RF modules that I've used before in previous videos, the NRF24L01, to control the servo motors and the Nerf gun from a distance. But anyway, so I'll go through this all in a future video if you really want to learn about these MOSFETs, these BJTs, and how to control motors with like something with microcontrollers. Again, I've also the Drone Workshop has a great video. So the DroneBot Workshop has great schematics, just a great YouTube channel. It's a great video to watch. They have this corresponding article which I've went through and highlighted some things. I'll go through that all in the future video if you're interested. But anyway, thanks for watching, and I'm going to try to keep this under an hour. So I'm at 59 minutes and 35 seconds right now. So thanks for watching. Again, if you follow the next video, I'll go over MOSFETs, different circuits, how to control a motor, turn on a light, so some high current light that you have in your house, and it'd be great. So, talk to you later.